12, 13,
Present, sir.
14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, roll number 26, 27, 28,
Present, sir.
Present,
20,
sir.
okay, 29, 30, 31,
Present, sir.
32, 33, 34, 35, 36. Right, Kirti is present. Anybody else?
Excuse me, sir.
Okay, Atiya. Right. Anybody else?
31, sir.
Tejas 51. Okay. Atiya is present. Anybody else? Okay. So we are discussing about the assignment questions. Next is question number 5. That is list the advantages of hybrid parameters. List the advantages of hybrid parameters. Okay. List the advantages of H parameters or hybrid parameters. So the advantages are you able to see the screen? Screen is visible?
No, sir.
Sorry, 1 minute. Now you are able to see? You are able to see now?
Yes, sir.
Okay. The first advantage is that H parameters are used to calculate the performance parameters. That is, they are used in the design and analysis of the circuits involving transistors. That is the first advantage. Second advantage is that as the frequency is less, in the design of the H parameters, right, reactance is very high. So it acts like a capacitors act like a open circuit. Therefore, the reactance part, okay, that is R plus JXL or R minus JXE, whatever you are writing, that reactance part, that is J part, is not present. It is 0 because of high value of reactance, open circuit. Therefore, they are the real numbers. We are getting the real numbers, which helps in the easy analysis of the H parameters. That is the second advantage at audio frequencies. Then these parameters are determined from the transistor characteristics. H parameters are determined from the transistor characteristics, and they are independent of the type of the transistor. Whatever equations we are deriving, they are independent of the PNP or NPN transistor. Both for PNP and NPN transistor, the equations are the same. There are the same equations. There are the same equations both for the circuits having PNP transistor and the circuits with the NPN transistor. Okay. Then one more advantage is that once the H parameters are obtained from the graph, right? Once the H parameters are obtained, they can be converted from one configuration to another configuration just by using the conversion formulas. There are certain formulas which convert the H parameters from one configuration to another configuration. For example, from common base, if you want to convert the H parameters to the H parameters of the common emitter configuration, then there are formulas for that, conversion formulas, which will convert the hybrid parameters in common base to common emitter hybrid parameters, like that. Okay, so these are the advantages of hybrid parameters, advantages of H parameters or the hybrid parameters. Okay, then coming to question number 6, define H parameters and obtain H parameter equivalent circuit of common emitter configuration. define H parameters and obtain H parameter equivalent circuit of common emitter configuration. This is explained in question number 1. While I was explaining question number 1 in the last class, I explained what is H parameter, why they are called as H parameters, right? What are the various equations for the H parameters? What are the standard equation, general equations for H parameters, and how to draw the H parameter model, hybrid model for common emitter, for common base, and for common collector configuration. That is explained in the last class, right? It is included in question number 1. This question number 6. Okay. Then question number 7. State and prove Miller's theorem. Okay. State and prove Miller's theorem. We have to explain the Miller's theorem here.
Sir,
Yes, please.
please allow it to play.
Yeah. Okay. 1 minute. Right. Sania is joining. Sania is joining. Rutik has not yet sent the call request, join request. Ask him to send the request immediately.
Yes, sir.
Manjunath Melligiri joined. Be fast. Call and tell him quickly.
Yes, sir.
Rutik Chopra joined. Okay. Right. Okay. Fine. So first we have to define the Miller's effect capacitance. This Miller's effect capacitance or the Miller's theorem is applicable to electronic circuits, right? Electronic circuits which are having the parasitic capacitance effects. Okay, the electronic circuits which face with the or which are having the parasitic capacitance effects, that is, they have the unwanted capacitances present in the feedback path. The capacitance, this CF, whatever is present in the feedback path between input node and the output node, because of that, the effect, whatever is produced, the loading effect on the input and output circuits, that is called as the Miller's effect. Okay, Miller's effect, and we are finding the equation for Miller's input capacitance and Miller's output capacitance. This is the feedback capacitance which is present between the input node and the output node, right? CF is the unwanted capacitance or the parasitic capacitance present between the input and the output nodes. Here we are first considering the inverting amplifier. For the inverting amplifier, the gain is negative. Output voltage is minus of the input voltage. That means the input voltage and the output voltage are 180° out of phase. Input voltage and output voltage are 180° out of phase. Now we are finding the loading effect of this CF on input circuit and the output portion of the circuit, right? Using the derivation here, we are finding the Miller's input capacitance and the Miller's output capacitance. To find Miller input capacitance, this is a circuit. II is the input current, V the input voltage Vi. Then I1 is the current entering into the circuit. I2 is the current flowing through feedback capacitance. Zi is input impedance. Ri is the resistance seen across the input terminals. This Zi is the resistance seen across the voltage input terminals, whereas resistance Ri is the resistance seen across the circuit input terminals. Then gain is V0 by Vi, output voltage is V0. Let Ri is equal to Vi upon I1. Ri, this resistance Ri, it is nothing but input voltage Vi divided by I1. Correct? Vi by I1. It is parallel. Vi divided by I1 gives the resistance Ri. Similarly, for I1 will be equal to Vi by Ri. We rearrange for I1. I1 will be equal to Vi by Ri. Then Zi will be equal to Vi by Ii, input impedance. Vi, input voltage, input current Ii, Vi by Ii gives the impedance Zi. or II is equal to VI by ZI. II will be equal to VI by ZI. If you apply Kirchhoff's current law at the input node, we have applying KCL, II is equal to I1 plus I2. II is equal to I1 plus I2 by applying KCL. Then what is I2? Let us find I1, I2. I2 is here the voltage is VI. Here at this node the voltage is V0. Therefore voltage divided by resistance, that gives the current according to Ohm's law. Therefore I2 will be equal to VI minus V0 divided by XCF. VI minus V0 is the voltage. XCF is the reactance or the impedance, right? Therefore VI minus V0 divided by XCF, that gives the current I2. That gives the current I2. Therefore I2 is equal to VI minus V0 by XCF. That is VI minus V0 is AV into VI. Output voltage equal to gain into input voltage, or gain is V0 by VI. Therefore V0 is equal to AV into VI. Substitute that VI minus AV VI divided by XCF. That is I2. Therefore I2 will be equal to, take VI common, VI into 1 minus AV, VI into 1 minus AV divided by XCF. Now substitute II, I1 and I2 in equation 1. What is equation 1? II is equal to I1 plus I2. II is VI by ZI, I1 is VI by RI, then I2 just now we have found out it is 1 minus AV into VI by XCF. So substitute that, we get VI by ZI is equal to VI by RI plus 1 minus AV into VI by XCF. Now here VI is common in both LHS and RHS. So VI will be cancelled out. Eliminating VI throughout, we have VI by ZI is equal to VI into 1 upon RI plus 1 minus AV by XCF. VI and VI will cancel. Therefore, we get 1 upon ZI is equal to 1 upon RI plus 1 divided by, here 1 upon ZI equal to 1 upon RI plus 1 divided by, denominator to denominator goes to numerator. That is 1 minus AV will come to the numerator. It will be same, 1 minus AV by XCF. That is 1 upon ZI is equal to 1 upon RI plus 1 divided by XCF by 1 upon 1 upon ZI is equal to 1 upon RI plus 1 divided by XCF divided by 1 minus AV. This I am writing it as 1 upon ZI is equal to 1 upon RI plus 1 upon XCMI. 1 upon XCMI. What is XCMI? XCMI is this term, that is XCF by 1 minus AV. Therefore, XCF is equal to 1 upon omega C. XC is 1 upon omega C. That is 1 upon 2 pi of CF. 1 upon 2 pi of CF. Substitute this XCF equation in equation 3. Okay. So XCMI will be equal to, XCF is 1 upon 2 pi of into 1 minus AV into CF. Or XCMI is equal to 1 upon 2 pi of CMI. What is CMI? This term, 1 minus AV into CF. Therefore, CMI will be equal to 1 minus AV into CF. Right? This is XCMI, or CMI is 1 minus AV into CF. That is Miller's input capacitance. Now this equation here, that is 1 upon ZI is equal to 1 upon RI plus 1 upon XCMI. It is a parallel combination of ZI is equal to RI and parallel combination of XCMI. That is drawn here. So ZI is nothing but parallel combination of CMI and RI. CMI is called the Miller's input capacitance. From equation 2, ZI can be interpreted as impedance resulting from parallel combination of RI and CMI. This is shown in the figure here. Next, let us find the Miller's output capacitance CM0. To find Miller's output capacitance, this is a circuit. We are assuming the output current as I0. This is getting split into I1 and I2. I1 and I2. Right? The resistance here is R0, and here the impedance is Z0. Okay. So I0 is getting split into I1 and I2. Okay. Now this current I0 is equal to I1 plus I2. Again, apply KCL at the node here. I0 is equal to I1 plus I2. What is R0? R0 is the output resistance R0. This is parallel V0 divided by I1. V0 divided by I1 gives R0. V0 divided by I1 gives R0, or I1 is equal to V0 by R0. Similarly, Z0, output impedance. Z0 is equal to output voltage by output current. That is V0 by I0. V0 by I0. That is I0 is equal to V0 upon Z0. Apply KCL at the output node. We have I0 is equal to I1 plus I2. Therefore, I2 will be equal to, what is I2? Here, this is the current which is flowing in the feedback path through the capacitance CF, that is I2. The voltage at this node is V0, voltage at the input node is Vi. Therefore, V0 minus Vi by XCF, that gives I2. That is I is equal to V by R according to the Ohm's law. I2 is equal to V0 minus Vi by XCF. Using Vi is equal to AV gain is V0 by Vi, ratio of output voltage to input voltage, or Vi is equal to V0 upon AV. Substitute that here in this equation for I2. We get I2 is equal to V0 minus V0 by AV by XCF. V0 common, that into 1 minus 1 upon AV by XCF. Now substitute for I1 and I2 into equation 1. Substituting for I1 and I2 into equation 1, we get. So equation 1 is I0 is equal to I1 plus I2. I0 is V0 by Z0. I1 is V0 by R0. Then I2 is whatever we have got here just now. That is V0 into 1 minus 1 upon EV by XCF. Okay, substitute here. I0 is equal to V0 by R0 plus V0 into 1 minus 1 upon EV by XCF. Now this R0 resistance is large. Usually the value of R0 resistance is large. Therefore, V0 by R0 will be very less. If you are dividing say 1 upon 100, you get 0.01. It is approximately equal to 0. Similarly, V0 by R0 will be very, very less, which can be neglected. Therefore, I0 will be approximately equal to V0 into 1 minus 1 by Y0 will be approximately equal to V0 into 1 minus 1 upon AV, that divided by XCF. What is Z0? Just now we have written the equation for Z0. Z0 is V0 by I0. Here we got the equation in the form of I0 equal to V0 into 1 minus 1 upon AV divided by XCF. V0 by I0 is Z0, that is XCF divided by 1 minus 1 upon AV. Z0 is equal to V0 upon I0, that is equal to XCF divided by 1 minus 1 upon AV. Therefore, Z0 is equal to XCF. What is XC? 1 upon omega C, that is 1 upon 2 pi f C. Substitute that. Z0 is equal to 1 upon 2 pi f into 1 minus 1 by AV. Z0 is equal to 1 upon 2 pi f into 1 minus 1 upon AV into C. Z0 is 1 upon 2 pi f Cm0. What is Cm0? It is 1 minus 1 upon AV into CF. Cm0 is 1 minus 1 upon AV into CF. What is this Cm0? Cm0 is the Miller's output capacitance. Cm0 is the Miller's output capacitance. Okay. What is the summary of Miller's theorem then? Summary of Miller's theorem is the capacitance CF which is connected between input and output node, that is feedback capacitance, will be converted as Miller's input capacitance connected between input terminal to ground, Miller's output capacitance connected between output terminal to ground. What is Miller's input capacitance? CMI is equal to 1 minus AV into CF. Then Miller's output capacitance is CM0 is equal to 1 minus 1 upon AV into CF. If we consider for non-inverting amplifier, that is output voltage is plus times the input voltage. V0 is equal to plus Vi, A into Vi. V0 is equal to plus A into Vi. That is, the gain is positive for the non-inverting amplifier. So for the non-inverting amplifier, this equation will become CMI is equal to 1 plus AV into CF, and CM0 will be 1 plus 1 upon AV into CF. That is what I have written here. Now, as I told, if you apply Miller's theorem, then the circuit will be the feedback capacitance, which whatever is connected between input node and the output node, that gets converted into Miller's input capacitance connected between input terminal to ground, and Miller's output capacitance connected between output terminal to ground. Okay. So this is the summary of the Miller's theorem. So we have defined the Miller's theorem. Right? What is Miller's theorem? So these are the points regarding the Miller's theorem. In the summary, we have covered that Miller's theorem, and we have derived the equation for the Miller's input capacitance and the Miller's output capacitance. The next question, question number 8, that is, then there is a numerical there. So let us solve that numerical. So this is the numerical which is given in question number 9. Question number 8 is same as that of question number 9, but beta is different. Okay. So question number 9, solve question number 9. So you all try for beta equal to that value, whatever is given. Okay. So this is with the beta equal to 200. This example, whatever I'm solving is with beta equal to 200. In question number 8, the beta value is changed and R naught is given, right, as infinity, and beta value is 100. Whatever is the value of R naught value is usually very large, say in terms of kilo ohms, thousands of ohms, or in terms of infinity, but R naught is not considered during the RE model, during the AC equivalent circuit, because it is a larger value, it is neglected, right? That is a neglected because of large value. For simplicity purpose, the value of R naught is neglected. Okay. Therefore, in the equations, we don't get the term R naught. In the equations, we don't get the term R naught. Okay. So either you calculate for question number 8 with beta equal to 100, with R naught equal to infinity. There is no equation with the R naught term, and similar in question number 9 also, it is a collector feedback configuration only. There is no equation with the R naught term, even though R naught value is 60k. Okay. So for this circuit, which circuit is this? This is collector feedback configuration. Collector feedback configuration, right? In the collector feedback configuration, there is a feedback between the collector to base. There is a feedback between collector to base, right? Then collector resistance is given as 2.7k, base resistance is 180k, emitter terminal is grounded, II is input current, then input voltage is V, output voltage is V naught. Okay, input impedance is Zi, and the current is I naught. For this circuit, it is a collector feedback configuration, both question number 8 and 9. For this I am solving for question number 9, this question, whatever I am solving here. Find the value of RE, Zi and Z naught, EV and AI. Consider beta equal to 200 and R naught equal to 60 kilo ohms. This is output resistance, R naught equal to 60 kilo ohms. IB equation is VCC minus VBE divided by RF plus beta RC. That is VCC minus VBE divided by RF plus beta RC. That is the equation for the base current. So you will have to memorize these formulas, that we know how to get these equations by applying the KVL to the input path and the output path of the circuit. Therefore, we get VCC is 9 volts minus VB is 0.7 volt, that divided by 180k plus beta is 200 into 2.7k. RF is 180k, RC is 2.7k. We get 11.53 microampere. Then I is 1 plus beta into IB, that is 201, beta is 200, 201 into 11.53 microampere. IB value, that comes out to 2.32 milliampere. Then RE is 26 millivolt by IE, this 26 millivolt divided by IE is 2.32 milliampere. This will be 11.21 ohms. Then we are finding ZI, input impedance. Formula for input impedance is small RE divided by 1 upon beta plus capital RC by capital RF. That will be small R is 11.21, that divided by 1 upon beta, that is 1 upon 200 plus capital RC is 2.7k, collector resistance, and feedback resistance is 180k. This will be 560.5 ohms. Then output impedance Z0 is RC parallel RF, it is 2.7k parallel 2.7k parallel 180 kilo ohms. This will be 2.66 kilo ohms. Capital RC parallel capital RF is output impedance Z0. AV gain formula is minus capital RC by small RE. Capital RC is 2.7k, that is collector resistance, divided by RE value small RE 11.21 ohms. This will be minus 240.86. Then current gain formula is minus AV into ZI by RC. AI is minus AV into ZI by RC. Substitute here. AV is minus 240.86 into ZI is 560.5 ohms. That divided by RC is 2.7k. This comes out to 50. Right. So this is how we are solving this collector feedback configuration circuit. This is a circuit for the collector feedback configuration. Okay. So in the question number 8, beta value is different. Okay, beta value given is 100. So you will solve for beta equal to 100. So values may be changed, and accordingly, whatever values are given, you have to see the values. Beta, whatever it is 100 or 200, and then solve the examples. Okay, what are the other values that are given? To see that, and accordingly, you have to solve the examples. So in today's class, we discussed the advantages of H parameters. Then H parameter equivalent circuit of common emitter configuration, Miller's theorem, right? Collector feedback, configuration of question number 8 and question number 9. I have solved the numerical of question number 9. The same will hold good for, the same is applicable for question number 8 also, but beta value is different. You have to solve for beta equal to 100. Here beta value is changing. Here in the equation the beta value changes here. Here we have used 200, but there it will be 100. So all the values will change here, right from the IB value. Okay, so that care you have to take there. Okay, so was it understood, students? Was it understood here? In the next class we will take up the next questions, that is remaining questions that we will take up in the tomorrow's class. Okay, any doubts here? Any doubts here, students? Was it understood? Ankita?
Yes, sir, understood.
Okay. Shraddha? Shraddha?
Yes, sir.
Understood.
Okay. Janvi? Rutik? Rutik?
Yes, sir. Understood, sir.
Okay. Rohan? Birje? Ratan? 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 Birje? Okay. So fine, then we'll continue the next class with the next assignment questions. Okay. Thank you.